Hi, guys. So I'd like to start today with one question. Have you ever tried to wish something into existence? Even if you were a kid or a teenager, did you ever think you had magical powers? Well, in this day and age, if you can think it, you can do it. And how do we do that? With 3D printing. Today's class is going to be so exciting. I'm definitely excited to be a part of it. We are going to be having Clarissa coming up here to talk to us about 3D printing. And afterwards, there's more. We're going to be talking about material analysis. Have you ever wondered how engineers know what to use for a car, an airplane? How do they know what to use to build those things? Today's class is going to answer all those questions. Welcome to our bonus class, guys. I hope you're as excited as I am because I'm definitely going to be staying for this class. Over to you, Clarissa.
Hi, hello everybody. I hope you guys are having a wonderful Saturday. Unfortunately, Kenneth has a family emergency and cannot speak with us this week. So I'm Clarissa and I'll kind of take over. Just a few reminders. Tomorrow, we will have a very interesting topic about space. A team from the Boeing company will talk about space debris, space environment, and satellites. And afterwards, we will take a 2-week break and resume on August the 1st. On the first Saturday of August, we're starting a new session about FLL and EV3 robotics software simulation hosted by FTC Team Second Rebellion. So it's very cool. Look forward to it, guys. And in the future, we tentatively have FTC programming, which will be presented by several FTC teams. Also, our topics will get a bit more difficult and more focused into stuff like intro to electronics. So a lot of things you can be excited for. Along with these topic-focused workshops, I think Code Orange will release several FLL and EV3 programming workshops or sessions. We'll release more information when the time comes. So don't worry, just sit tight, and we have a lot in store coming for you guys. Just a reminder, we won't have a CAD session this week, but a CAD video will be made available so you guys can practice at home. And with that, let me get into introducing the presenters. This week we have FRC Team 3476, Code Orange, from Irvine, California. These engineers are extremely talented. Code Orange is one of the most successful robotics teams in our area with a world championship division win and a blue banner as well. It is my honor to introduce X and Scott from Code Orange. Oh, yeah.
Good afternoon, everyone. My name is Scott, and then presenting with me today is X. So first, we'll go into a little bit of an introduction about ourselves. Can I get the next slide, please? So we're from Team 3476 Code Orange. We are, as Clarissa mentioned, a FIRST robotics team located in Irvine, California. You can find this by our neon orange shirts that I'm currently wearing. And we work with mainly high school students, but also middle school students in the surrounding areas. Yep, next slide, please.
Hi everyone, I'm Ike's son. I'm an undergraduate student at University of California, Berkeley, studying mechanical engineering. I'm going to present you something about 3D printing today, and hopefully gonna get you excited about its technology. And Scott?
Hi everyone. So as mentioned earlier, my name is Scott. I am a automation design engineer at Applied Medical, and I got my bachelor's of science from UC Irvine. And so what Clarissa is playing right now is a little peek into what I do as a day job. I get to make robots for a living. right, cool. Thank you, Clarissa.
Yeah, so I will begin the presentation with 3D printer. So basically this presentation, the main thing I want you guys to know is the diversity of 3D printing and many types of 3D printers. So when I first started about learn about 3D printer, I thought it is only like the machine that I have seen, but after I got into it, there are actually many different types of machines that can 3D print. There might be some concepts that you don't fully get that's entirely fine, because what I want you to get from this presentation is really to get excited about this 3D printing technology and maybe think more in the future and maybe change the industry with your knowledge in the future. Next slide, please. So we'll begin with some types of 3D printing. So this is the first type we're going to introduce. It's called filament deposition modeling, short for FDM. It is the most common type of 3D printing. You can see how it works is there's a filament coming from the back of the machine, goes into the extruder. This is a filament going into the extruder that would melt those filament and print layer by layer of those modelings. The speed those materials solidifies really fast. So as soon as it drops on the model, it basically solidifies. A lot of people using that right now. Many people have them at their houses. I actually have my own FDM machine. Just got it like a couple weeks ago, and many universities have those in their makerspace. It's really handy when it comes to practice for engineering students for prototypes. There are mainly two materials that we use with FDM 3D printing. One is called PLA. It is more environmentally friendly. You can usually get 1 kilogram for $20. Another type of material is called ABS. It's more strong, but might be toxic sometimes. And it's usually used with for bigger machines. Yeah, let's go to the next slide. Next type of 3D printing I want to introduce you is called stereolithography. They use some sort of liquid resin, as you can see. In those resin, there's some chemical components that can be solidified after they meet UV light. So those components called, I think it's called photoinitiator. They are mixed with polymers, and that is the main components of resin. And you can see those geometry can be really just printed by this stereolithography, because if we use FDM machine to print those, you need to have some sort of support material under those overhung structures. And because this structure only has those holes on their surface, it would be really hard to get those support material out. So, but in stereolithography, you can just make those holes and the liquid will just flow out after you print those. So it usually gives higher resolution than FDM, and it can print more complex geometry than FDM. Let's go to the next slide, please. Next slide is called selective laser sintering. It is a type of metal printing. It is the most common industrial metal printing. So this is a powder bed. They have basically metal powders, and then they use the same laser to solidify those metals layer by layer. After they print one layer, they would cover the layer with new powders again. Usually, you will need some sort of binding, some sort of plastic in this powder bed, not just metal powders. So usually what you do after this is printed, you have to melt the part. Usually the plastic melt, so there are pores in the object after you print it. So that's a big disadvantage, but we don't really have better technology right now because metal usually has really high melt point. So if you want to print them fast, you need to have plastic inside of those powders. Next slide, please. Next technology is called Polyjet. It is really just used by one company, so it's not as general as those before it. but it is really cool technology because you can use multiple color, multiple materials, and this is super fast and it can give really high resolution. How this works is really like just your normal printer. Normal printer they eject ink, but this one it eject different materials basically for 3D printing. So that's why it can eject different multiple colors, multiple materials very easily compared with others. However, usually those type of 3D printing, they cost a lot of money because the material is more expensive, and how you manufacture those materials are more expensive because you have to make them into droplets to eject them from the 3D printer. Can we go to the next slide, please? So I hope you really enjoy those types of learning, those type of 3D printing. I want to show you some really, really cool stuff that you can do with 3D printer so that you can get excited about it. So at home, people are getting really creative about 3D printing. They can really 3D print everything, mostly from their house, sometimes from some industrial company. But those are some things that can be done by 3D printing really well. So you can see this is, yeah, a lot of people make hands and legs for people who unfortunately lost them. And those legs and hands are really personalized. So it's really big advantage of 3D printing to print whatever shape that you want. And this is really cool thing to give your roommate. Let's see, we'll go for a couple more seconds and then we'll switch. Yeah, a lot of people just print a lot of modelings to decorate their house. And you can see in this one, you can actually paint 3D printing parts with PLA, at least I know. Yeah, a lot of companies use 3D printing to print their logos. This is a doorstop that you can just print with in home if you have a 3D printer. And yeah, it's something cool to make your mom if they break their legs. Let's see. Oh yeah. So next thing I want to show you is those gigantic robot arms that are used in industry to actually print rockets that are just super cool and very excited. They are usually used to make rocket engines. They are using metals. It's like an extruder, but I think they hate it for higher temperature so they can print more pure metals. As you can see, they can print really big engine, really big. And those robot arms, because it can rotate to various degrees, so it can actually reach many weird angles and to make really fine details. Next slide, please. Oh, and if you're interested in those videos, YouTube has a lot of those videos. So next thing, it's really hard to just ignore the global background when we give the presentation now. But some good news from this pandemic is a lot of people are really using 3D printer to help saving lives. Many people are printing face shield straps for health workers and printing face masks for themselves, for their friends. And that's something that you can really do at home, and you can print those and donate them to some certain organizations, and those organizations will help you to distribute those to different places in the world. Actually, Code Orange just printed a lot of those face shields for many health workers in California, and yeah, I just really want you to know the power that you can have and the cool things you can do with those 3D printers. Those are door handles. A lot of people are talking that you don't have to use hand to open the door now. Yeah, let's go to the next slide, please. So this is a really cool technology I really want to show you because I'm working on this technology right now. But this is mainly from my professor. I saw it in my freshman year orientation, and I just fall in love with it immediately. It is really cool because normally how stereolithography works and how other 3D printer works is it print layer by layer. But this one, because it has a rotating bottle of resin, it can actually print actually 3D. So ideally, every point in this model would form at the same time so that you can have a lot of material advantages, meaning because if you have those two layers, it sometimes just have those shear forces, it just break it. But if you have those two layers really as one layer, then it becomes much stronger. And as you can see, they nicknamed that replicator. In the future, we're really hoping that we can take whatever photos that we want of a real world object, and then you put that into the projector, and the projector is gonna project UV light that solidify those resins in the rotating bottle, so that you can just print whatever really you want. And this is how they take photos and put them into projector project UV light to the resin, and then the parts solidifies based on where the UV light shine in. This sort of thing also needs a lot of software skills, a lot of optimization, what they called. Yeah, we can go to the next slide, please. I hope you're excited about it. Technology is really cool. And after we have learned something about 3D printing, I want to invite you to all think why we really need 3D printing, why we cannot just create those skills, those objects with other manufacturing processes. So first, I want to introduce you to other most common manufacturing process. One is subtractive manufacturing. It's really just cutting stuff out of a block of metal, let's see. And another process is called injection molding or casting. Casting is very similar to injection molding. It just injection molding is for plastic and casting is for metal. Let's go to the next slide. So I want to show you this video about subtractive manufacturing. So you can see it's really just you use a lot of very cool tools to cut those big block of metals. Let's see, something called CNC machine. It's a computer controlled. You can create a program that can program those tools that to tell them where to go, where to cut. Let's see here. It's very common, not very common, but many universities and FRC teams have those CNC machines. It just comes to really handy and more accurate than human cutting them by hand. So you can see they just cut them. So they just cut that into this shape. So you can see if those shapes are really clear as a surface, they don't go to more complex. It's very handy to just use subtractive. It's much faster than 3D printing. But when it comes to more complex shape, it's not a good idea to use subtractive sometimes because you have to create really accurate tools that maybe cost a lot of money. And many other reasons that I'm going to show you later. Can we go to the next slide, please? So next slide, I'm going to show you a video of injection molding. Can we go to the middle of the video again? So injection molding is basically you have a shell, and then you eject either liquid plastic or liquid metal into the shell, and after it solidifies, it just becomes whatever parts that you want it to be, whatever shape. So most plastic object that you're using right now is really made by injection molding because it just so cheap after you make the tools, make the model. Usually the model is the most expensive part, but after you make the model, each part maybe just costs a couple cents. So you can see the red part is the melted liquid plastic, and they're ejected into the mold. And then after it's cooled, the cooling process time is usually really fast, especially if there are small parts and they are ejected. Yeah, so that's how injection molding works. Casting for metal works similar way, but a little different. Next slide, please. So after we learned the subtractive manufacturing and the injection molding, I really want to show you why we choose 3D printing in some manufacturing processes. So first advantage is really the personalization, customization process. So you can see this man. If you can guess what this man is holding, you're probably not gonna guess. He's holding a 3D printed human heart. It's a little small, but it is a prototype, I think. So one of the biggest application of 3D printing right now is really buyout printing. A lot of people are trying to print their cells and kidney, like heart, lungs, for people to replace their own. Sometimes when people are sick, they have to replace some of their organs, but if they have to wait for some donations. They maybe have to wait for a really long time, sometimes decade, and they don't really have time to wait for that. So 3D printing is really trying to customize those for those people who need to replace their organ. So for example, if I need a heart to be replaced, they can take a cell from me and then just print a heart that would just fit right into my body, so my body is not rejected. That just increases safety so well. Next slide, please. So next advantage of 3D printing is really comes to the complex geometry it is. So if you see the rabbit, can you imagine you just cut this rabbit from a big block of metal? It is maybe achievable, but would be really complex. You need really high tools. But if you use stereolithography, let's say, it would be super easy. It may take time, but it would be much easier. And on the right hand side, you can see those geometries. They are sort of like engine. So another big application of 3D printing right now is they print engines and parts for airplanes. So if you imagine if you wanna cut a big engine that's gigantic from a big block of metal, you need a really big block of metal. So usually people do is they cut two parts, then they put those two parts together by melt the edge of those two parts and then just weld them together. However, if you use 3D printing, it would be much easier to print those gigantic parts. And also you can print more complex geometry if the engine needs, and that means less failure because those metals, they're melted together instead of melted them after you cut them. Next slide, please. And next advantage is really supply chain. That means you can use the 3D printing in space with an advantage. So supply chain means basically you supply the raw material to your manufacturer. So if you think about it, in Mars, if you supply like 1 kilogram powder to Mars, maybe they can print something pretty cool. But if you bring this whole house to Mars, you need a lot bigger spacecraft, and it'll be quite wasting of time that you make them on Earth, then you put them on Mars. But if you just bring the powder to Mars, you can print whatever you want. And this is another application of 3D printing right now. Many people are making houses with gigantic, just robot arms with 3D printing. Next slide, please. So I believe the last advantage I want to introduce you is really prototype. A lot of college engineering students use those, including FRC students, use those to print parts that they want to test, because you can see them really fast. You can figure out, are they actually working really well? Are they not? If they're not working really well, you can just change the model on your computer and then print them again, because this process doesn't cost a lot of money and it's really easy to access 3D printing in many regions right now globally. So a lot of people are really using those to prototype. And next slide, please. So after we learn those advantages, I want you to think about how maybe we can change this industry in the future, maybe improve them. So the biggest challenge in 3D printing those time is first is time. It takes a really really long time to print a same part that you can make by injection molding or subtractive manufacturing process. Also, it uses a lot of power, so that means not really environmentally friendly. And material, you're very limited by material. First, it's not environmentally friendly if you use a lot of plastic. And another thing is there are just not many properties that we can make with 3D printing materials that have desired outcomes as engineering want. So you maybe can use much better materials if you use subtractive or injection molding manufacturing. So I want you to think about maybe in the future how you can improve those. So some of the really futuristic 3D printer you can see on the bottom, it is a meat 3D printer. So many people are using 3D printing to print meat with soil, with beans. Sorry, this is a meatless meat. So using 3D printer, a big advantage is really making the texture really like the real meat. And that's some really new technology actually. And I also thought about what if you make 3D printer and flying robots together, which means you can use different materials, different colors, with different flying robots, and then they just collaborate together and print one thing. Then you can really have different materials, different colors, and you can basically reach every point where you want to print. So next slide, please. That comes to the end of the 3D printing slide, and I really want you to know that innovation is the key of the future, and you can help to either shape this industry into a better shape, or you can help if you are able to access to a 3D printer to help with the global pandemic or future opportunities that need your help. And yeah, let's go to slides, Scott slides.
All right, thanks, X. So in my section, we're going to be talking about material analysis, basically using the right materials at the right time for the right purposes. And so that's the overarching goal that I want you guys to take away, is knowing what materials are generally good at certain things. Okay, the next slide, please. So a main question I want you to think about through this section is, when creating something, have you ever asked yourself why we're using that particular material? So again, just think about this as we go through. At the next slide. So some general categories which we group materials into are things like wood or metals, ceramics, plastics, and then since we talked about 3D printing, we're also going to throw 3D printing in with this presentation as well. Next slide. So the next 5 slides are going to be asking some questions. And so as we go along, I want you guys to think about, or if you know these answers, feel free to pitch those in the live comments. But if we have some time at the end, we'll go over why these objects use these materials. And so the first question is, why do cars use metal, and why not use a plastic frame since it's cheaper? So again, just think about these as we go along. How come we don't have plastic houses? Why do we see homes using brick or wood or stuff like that? Have you ever seen a chair made out of ceramics before, or mainly wood or mainly plastics? And then have you ever seen a car with a car intentionally have a plastic windshield? Why is it usually glass? And then we have one more. Have you ever seen a wire made out of wood before, and has it worked well? So again, different materials have different properties, and we'll go over those as we go along. Next slide, please. So the first slide here, we're going to be going over stress and strain. So basically telling us how strong these materials are and how resistant they are to different changes in their environment and when we push and pull them. Next is their properties. And then last, we'll go over why is this information even useful? And so we'll go on to the first set, which is talking about what is stress. So stress, as defined by the dictionary, is the amount of force on a small area inside of the material. So really, what this breaks down is how much force an object experiences when we pull or push on it or bend it. So the very basic formula for this is stress is equal to the amount of force divided by the cross-sectional area. And stress is usually denoted as the letter sigma, which is like the circle with the line on the top of it. So one thing to keep in mind as I go through the first chunk of slides here is that, yes, knowing the equations is very useful. But to be perfectly transparent here, I don't use these equations in my day job. Even though I know the information, what's really more important is understanding how these equations, what they mean in real life. So in this case, stress really depends on the amount of force, but also depends on the size of the object we're putting the stress on. Can I get the next slide, please? So as mentioned earlier, we're going to be going over some more equation kind of things. So in this slide, we're going to do a quick example. So say we have a cylinder that has a diameter of 1 meter, and we apply a force of 1 Newton to the end of the cylinder. So basically, imagine you have this rod in your hands, right? And you pull out the ends at a force of exactly 1 Newton. And so we can use our equation from before. Stress, or sigma, is equal to force divided by area. And we know the force. And then the area can be calculated by a simple area of the circle calculation. So in this case, it's 1 Newton divided by 0.7854 meters squared, which is equal to 1.273 newtons per meter squared. And if you remember from a previous section, that we can use newtons per meter squared and also reference it as pascals, a unit of pressure. Okay, next slide, please. So along with stress, we also need to learn what strain is. So strain basically tells us when we pull on an object, the object wants to stretch out. If you've pulled on like a piece of cloth or a rubber band or stuff like that, you notice that they do stretch out when you apply a force. So strain tells us how much or to what degree that material has deformed. So for strain, again, there's an equation for this. It's the length of the fully stretched out object minus the original length divided by the original length. So ultimately, this gives us a percentage of stretch increase or length increase. And that's very useful in a future slide, which we'll go over in a bit. But first, let's go over an example. Can I get the next slide, please? So similar cylinder, we have a cylinder that's 1 meter long. And once we pull on it, it becomes 1.5 meters long. So using our equation, we have our new length, which is 1.5 meters, subtracted from the original length, which is 1 meter, divided by the original length, which is 1 meter. And it gives us 0.5 meters divided by 1 meter, which the units will cancel out, and it'll give us a strain of 0.5. So I know those are very, very arbitrary values, and the next few slides will connect those really random values and put a meaning behind them or meaning to them. In the next slide, please. So this is going to be our friend for the next 10, 15 minutes. This is a stress strain curve. It relates stresses on the y-axis to strains on the x-axis. And so we'll be going over the different chunks of those shortly here. Next slide, please. So this first section, highlighted in the red circle, is the elastic region. So when we pull on an object, right, sometimes it'll retreat back to the same size. And that's what the elastic region tells us. Usually for most materials, the uppermost amount of stress that you can apply to material is called the yield strength. And a simple Google search will tell you the yield strength. So say like I wanted to look up the yield strength of aluminum. Going into Google and asking that will provide you an amount in gigapascals. If you remember earlier, pascals is a unit that we use to describe stress. So it'll tell us how much stress and kind of how much strain we can apply to these objects or these materials before they break. Next slide, please. One other thing before we move on is something called Young's modulus. And what Young's modulus does is it relates stresses to strains. So the equation here is stress is equal to Young's modulus times strain. You can figure this out empirically by getting a stress strain curve and then measuring the slope of the elastic region. I don't suggest you do it. It's probably not going to be very accurate. Usually Young's modulus can be found in a table or a diagram of some sort by scientists who have already done this work. Next slide, please. Okay, so the next chunk of the stress strain curve is called the plastic region. So the plastic region says that anything beyond the elastic region, we're going to have permanent deformation or permanent stretching. So say, I'm sure you all have seen this before, where you've pulled on something and it came back to the same size, but then you pulled too far on it and now it's no longer able to go back to the same size again. So that's what the plastic region is. It's permanent stretching. And also if we look at just the graph here, usually you'll have a lot more stretching in this section versus the elastic region. So again, if you look at the strain portion, you really don't gain that much strength or that much extra stress that you can withstand, but man, it really does stretch out in terms of the amount of strain you can see. Next slide, please. So one other point, so we had yield strength in the elastic region, but in the plastic region, we have ultimate strength, which is the maximum amount of strength an object will be able to withstand. Usually, in most cases, engineers will use yield strength as our determination of whether or not a material is good enough for the job that we're doing. And this is because, so imagine you had this really, really tall building, right? And it withstands amount of force, say during an earthquake. If we relied on ultimate strength as our unit or as our boundary here, we could have a building that may stand up, but may also be, I don't know, 5 or 10 meters bigger than it was before. And that's really not something you want or something that you can trust. So really, for most cases, and when determining the amount of or stress or the durability of an object, we really want to use yield strength, but knowing ultimate strength is good to know as well. Next slide, please. So I've been talking a lot about numbers and graphs and whatnot, but I think now's a good time to bring in how we actually test these materials. So we have a short video about how we actually test these things.
Material with yield point phenomenon. In the first tensile test, a plain carbon steel with yield point phenomenon is to be tested. This is the test piece. It has a cylindrical test region with an original diameter of 10 millimeters and an original gauge length of 100 millimeters. Within this test region, distance marks have been drawn at regular intervals. They help to visualize and measure the plastic behavior of the specimen. Using a hand control, the tester moves the upper crosshead into its correct starting position. Now he can place the threaded ends of the test piece in the lower and upper grips of the testing machine. In the next step, he swings the extensometer into its working position and checks that everything is correctly prepared. Then he selects all necessary testing parameters on the control computer. Ready. The test starts, and the extensometer's sensor arms are carefully pressed onto the test piece. This way, the gauge length can be measured throughout the whole tensile test. The gauge length is displayed at the bottom right-hand corner of the screen. At the beginning, it amounts to 100 millimeters. During the tensile test, the test piece is slowly and constantly elongated with a standardized speed. The force that the test piece opposes to the imposed elongation is recorded and can be seen at the bottom left-hand corner of the computer display. The material behavior can best be observed in a force elongation diagram. The force F is being plotted upwards on the vertical axis, the elongation delta L towards the right on the horizontal axis. At first, the force rises rapidly. Force and elongation are proportional and form a steep, straight line in the diagram. In this area, the material behaves elastically. If the test piece were to be unloaded from this area, it would spring back completely to its original length. In materials with yield point phenomenon, the end of the elastic area can be seen clearly. The plastic deformation starts abruptly and is accompanied by a sudden drop of force. If the test piece were to be unloaded now, it would not spring back to the original length, but instead show a permanent elongation. In the next stage of the tensile test, an almost constant force level with slight fluctuations occurs. This phenomenon is called the Ludus Effect. After a certain strain, known as the Ludus strain, the force increases again. The material opposes an increasing force against the imposed elongation. It strain hardens. Up to the point of maximum force, the test piece is strained uniformly along its length. This means that the test piece gets longer and thinner, but keeps a cylindrical shape. As soon as the maximum force is reached, a neck begins to form at one point of the test piece. All further plastic deformation now only takes place at the neck, and eventually the test piece fractures there. In the recorded force elongation diagram, the force FEH at the upper yield point can clearly be seen. This is the highest force the test piece can sustain elastically. FEL
Hey,
is
Clarissa, can you
defined
pause
as
the video right there?
at the lower yield point.
Thank you. Okay, so again, this graph, which they made on their own with their own testing equipment, looks very, very much like our stress strain curve. Because you have the elastic region, you have the plastic region, and then the very tail point is the fracture point. And so this is how scientists will test different materials and find out what their yield strength or what their plastic deformation range looks like. And that's how we kind of figure out these values. Next slide, please. So now we know the general basics. Let's talk about individual materials. This slide should look familiar. It has our wood, our metal, our ceramics, our plastics, our 3D print groupings. And we'll go over each of them and their different strengths and their different weaknesses. Next slide, please. So first up is the metals category. These are going to be some generalizations about the category. They're not, you can find metals with varying properties. And that's going to be the case for most materials. We're going to be going over generalizations, but not specifics. Because ultimately you can find a super lightweight metal that's probably lighter than the heaviest plastic. But again, some generalizations. They tend to be pretty strong, but they also tend to be pretty heavy. And one of the cool things about metals is that you can mix different elements or different metals together to get whatever properties you really need. So say you don't want something to rust. You can add in different compounds to make a non-rusting stainless steel. Or say you want conductivity. So say you want to transmit electricity from point A to point B, then you're going to want something, say like copper, who has good conductivity. So again, metals are very, very, they can do a bunch of different things, but ultimately, compared to other materials, they're pretty pricey, and they're pretty heavy. Can I get the next slide, please? Next up is wood. So some things about wood are that it can be strong, but only in certain cases. And if we look down at the bottom right, we have another stress strain curve. And you can see that they tested the same type of wood, the same wood board, in different ways. So the way wood works or grows really is that you have layers in the trees, right? And so if you pull on the ends of the layers or push on the ends of the layers, you get a pretty strong material. But if you start splitting the layers, then it just kind of falls apart. So when you're using wood, you need to think about what directions you're fastening the wood with, or what kind of forces you're going to see on your projects. So some other things you can look at here. Again, you can find really, really heavy wood or really, really super light wood as well. Materials can fluctuate between the top ends and the bottom ends of the spectrums in terms of their generalizations. But generally, they're pretty lightweight, and they're relatively cheap. You can find wood basically anywhere. You can find it in a tree, really. Next slide, please. Plastics are next. Again, some generalizations about plastics. Pretty lightweight, and they are engineered to be one of the most versatile materials. So some things to think about. You can have a material that's super, or a plastic that's super, super stretchy, or you can have a plastic that's super, super tough. And it depends on the chemical composition of these plastics, and that's why people make lots and lots of money as chemical engineers that design these plastics, because they can be so different depending on their chemical makeup. So some other things one thing about plastic is that if you are creating plastic objects one at a time, it's going to cost you a lot. But as X mentioned, if you're doing injection molding, it's so cheap. Like you can see a plastic bottle everywhere, right? And those don't cost you a fortune to have. So something to think about is volume is important with plastics. The more you make, the cheaper it is, as is with most materials, but even more so with plastics. Next slide, please. So next up is ceramics. So we're thinking like the same ceramics as like a clay vase or a pot of a certain of clay varieties, and they're really strong and they're really great, and they work until you drop them once, at which point they're no longer useful to you and they're in like a million different pieces. But again, they're strong until they break. As you can see on the space shuttle over here in the top right, we put them on the space shuttle because of one of their main characteristics or generalizations about this material, is that they are very, very good at heat absorption. So instead of burning up the space shuttle on Earth re-entry, the clay tiles will absorb the heat and keep the heat to themselves instead of transmitting it into other more delicate things. But again, main downsides of ceramics, if you look at the bottom right, we have a stress strain curve for ceramics, or in this case, brittle materials in general. They have a elastic region, but they really don't have a plastic region, because as soon as you hit a little bit beyond yield strength, they're going to break on you. So if you're going to see, or if you want something to last for a very long time, or if you're afraid of someone dropping your project and you want that project to stay in one piece, maybe don't use ceramics. But it's ultimately pretty cheap. You can find clay anywhere. You can mix clay, and it's very easy to manufacture with. You can just even use your hands. I'm sure some of you all have made clay pots or cups before out of clay. Next slide, please. So last up, we're going to talk about 3D prints. If you use the same plastic and you make the same, say, well, we use a plastic bottle, like a water bottle, for example. If you make the same object from a 3D printer versus, say, injection molding, the 3D printer will always be weaker. And that is because of the manufacturing process behind it. The manufacturing process for a regular average plastic bottle is just one uniform piece of plastic. But as soon as you start 3D printing, just like wood, you have layers stacked up on top of each other. So we have to be very careful about the way at which we expect these things to work. So again, if you look at the stress strain curves on the right, each of these it depends, the stresses that we can withstand depend on the amount or the way we orient the part. If we're pushing and pulling on the layers, probably okay. But if we're applying a force that splits apart the layers, your 3D print's going to break apart very, very quickly. So again, just keep these things in mind as you're doing your projects. The way materials are formed is critical to your success of the project, as well as the type of materials as well. So some other things about 3D prints as well. You can make any shape, really. As long as you have a 3D printer, you're good to go. In terms of price, the printer up front is going to be pretty expensive. And it is getting cheaper, but it's still not a commodity. It's still pretty expensive. But every print after that, it will be relatively cheap as you're just getting the material or using material at that point. Let's see. I think that's it for me. If you want further information about Code Orange, you can visit us at teamcodeorange.com.
Yeah, I think with that, that concludes our presentation on 3D printing and material analysis. So I hope you guys had a great time learning something a bit different this week. With that, I'll pass it back to Victory to tell you what we'll be doing next.
So this month, this is back.